So today we're going to talk about concentration of solutions again, this time pertaining to dilutions and solution stoichiometry specifically associated with ions. So here we're going to talk about dilution, which is the process of preparing a less concentrated solution from one that is more concentrated. Sometimes these more concentrated solutions are called stock solutions. They're prepared far ahead of time, and you can create more dilute solutions from them. One example of this is, here's a very concentrated stock solution. You can put a very small amount of that, let's say 10 milliliters of this stock solution, into a new container for measuring volume. Add a bunch more solvent in order to dilute it. So then you would create this sort of solution here that's more dilute. A lot of times you're going to see this called M1V1 equals M2V2. The whole idea here is that the moles of solute from this first 10 milliliter solution of the stock solution and the entire, let's say, 100 milliliter solution that has now been diluted, the moles in both situations are equivalent to each other. Okay, so because of that, moles of solute equals your molarity, which remember is moles of solute per liter of solution, times your volume, your liters of solution. Okay, so that's molarity times the volume. Here we're saying molarity times the volume is in liters, so that's why they're calling liters. So, and the C is with reference to concentrated. So again, a lot of times you're going to see M1 times V1 equals M2 times V2, where V is volume in liters, or as you can see, it could be in milliliters in both situations. And M1 and V1 is with reference to the first solution, which is our concentrated solution, or our stock solution. And then M2V2 is with reference to our diluted solution. Okay, so this is the general setup. And again, we can do this. We can say molarity times volume equals molarity times volume because that's equivalent to moles of solute. Moles of solute from our concentrated solution, however much we chose to use, in this case 10 milliliters, is going to be equivalent to the moles of solute in the diluted solution. It's just we added a lot more water to it if the solvent was water. All right, so let's try one of these. What volume of 12 molar hydrochloric acid, a common lab stock solution, must be used to prepare 250 milliliters of a 0.125 molar hydrochloric acid solution? Okay, so 12 molar hydrochloric acid, that's also nominally called concentrated hydrochloric acid. So like I said, this is a common stock solution, but most of the time we don't use such a concentrated acid. We want to create more dilute hydrochloric acid. So this would be a lab method for doing that. It's via a dilution. So we write what we know. In this case, our M1V1 is with reference to our stock solution. So our molarity of our stock solution is 12.0 molar HCl. We're trying to find out how much volume of that stock solution we will need to use to create this other diluted hydrochloric acid solution. So our M2V2 is with reference to what we're trying to create. The molarity of the second solution is 0.125, and the volume that we are aiming for is 250 milliliters. So we just need to solve for V1, right? The volume of the first solution, the stock solution. Since our V2 is in milliliters, V1 will also be in milliliters. So we can just rearrange that equation algebraically to solve for V1, and then we just plug in everything that we need. M2, V2 multiplied by each other divided by M1, and that will get us 2.60 milliliters of that 12 molar hydrochloric acid solution. So again, I have a big amount of this concentrated hydrochloric acid solution that is 12 molar. I would take out 2.60 milliliters of that solution, and I would add it to a volumetric flask that is 250 milliliters total in volume. And then I would add water to that until I reach exactly 250 milliliters. And then I could say with confidence, I could label that new solution that's 250 milliliters. I could say with confidence that that has a concentration of 0.125 molar with respect to hydrochloric acid. Okay, so that's the idea here. Again, the only real mistake that I see folks making are mixing up the two molarities. We just kind of slap in the molarity which way. If you ended up getting a volume that was much larger than 250 milliliters, you know that that has to be not true, right? You can't create a 250 milliliter solution with something that's far larger than 250 milliliters. So this really does have to be much smaller because you're with reference to the V1, the more concentrated solution. So that would be the only mistake that I commonly will see here. All right, we'll try another one. This is what I had mentioned before in terms of a serial dilution. So we could create different standard solutions. The serial dilution is a way to create very dilute solutions without trying to measure a very tiny volume of the concentrated solution. So we'll do it iteratively. We'll do this many times. So we start with a 2 molar stock solution of hydrochloric acid. We're going to try and make 4 standard solutions prepared sequentially by diluting 10 milliliters of each solution up to 250 milliliters. Okay, so we're going to determine the concentration of all 4 standard solutions and the number of moles of HCl in each solution. We're actually not going to do that part B necessarily, but remember, anytime we use M1V1 equals M2V2, the moles of the first solution and moles of the second solution do need to be equivalent. Okay, and then so on and so forth. We're going to do that again. So again, the moles should be equivalent in the second situation as well. All right, so we'll start with that first one. We're taking just 10 milliliters of that 2 molar concentrated solution, and we're going to dilute that to 250 milliliters. So we're going to try and find the molarity of that second solution. And I say second solution, really that's going to be called solution number 1, the first standard solution. And then just M1V1 equals M2V2. We solve for M2. That's the one equation, one unknown, so that is solvable. And we just plug that in. So 2 molar solution times 10 milliliters divided by 250 milliliters. This should give us a molarity of hydrochloric acid for our new 250 milliliter solution. So we get 8.00 times 10 to the negative 2 molar HCl. We're calling this solution number 1. Okay, so that's our first standard solution. You can see we diluted it. It is now much less concentrated than our original standard stock solution of 2 molar. It's significantly more dilute, 25 times more dilute. So we're going to call this solution number 1. Now, somewhat confusingly, is we will not have 250, we have 250 milliliters of the solution currently, but in order to do this standard dilution, we're going to take just 10 milliliters of solution number 1 and do this again and dilute it up to 250 milliliters. That is this serial dilution or sequential dilution. Okay, so this is the new M1. We're just going to use M1V1 equals M2V2. So we're just going to plug this new thing in as M1. And again, we're only taking 10 milliliters of that solution. So this is kind of the new setup for standard solution number 2. M1 equals what we just found. We're only taking 10 milliliters of that. We're going to try solve for M2 again, knowing that we are diluting once again up to 250 milliliters. Now we're going to do this 4 times. I'm not going to show all of those. So that means solution number 2 is 3.20 times 10 to the negative 3rd molar with respect to hydrochloric acid. And then again, that would now become our M1, and our V1 would still be 10 milliliters. Our V2 would still be 250 milliliters, and now we'd solve for M2 again. If we were to do that again, we would get 1.28 times 10 to the negative 4th molar hydrochloric acid, and then yet again to 5.12 times 10 to the negative 6 molar HCl. So you can see we dramatically reduced the concentration in each step. And none of these are actually that hard to measure. 10 milliliters is not very hard to measure. And then dilution up to 250 milliliters also is not very challenging. So this is a very simple lab method for getting these much more dilute solutions. So the final goal was solution number 4, actually. So kind of a question could be, well, again, okay, let's talk about B. So the number of moles of HCl in each solution. The whole idea here is that if you were to take anytime you do M1V1 equals M2V2, the moles of that first solution do need to equal the moles of the second solution. Okay, so that should all be the same. Of course, once you have 250 milliliters of something and then you're only taking off 10, that will be a 25-fold reduction in the moles of hydrochloric acid. Okay, so let's say I just wanted to make solution number 4. How come I couldn't just take my 2 molar hydrochloric acid stock solution and immediately dilute that all the way down to solution number 4 instead of skipping these 3 intermediate steps? So you could do the math for that. I did that for you, but I found out that if you were to try and do that, you would have to do 6.40 times 10 to the negative 4th milliliters, which is a tiny, tiny volume. It's like half a microliter of solution. It's pretty hard to measure that. It's not that it can't be done, but it's pretty hard to measure such a tiny, tiny quantity of hydrochloric acid. So because of that, it's not a very accurate measurement. So we would not have high confidence that we were actually getting down to 5.12 times 10 to the negative 6 molar. There would be much larger error bars associated with that. So this is part of the reason why we do this standard serial dilution. All right, so now we're going to move on to solution stoichiometry in reference to concentration of solutions. So this is an idea we have dealt with before. So here's sodium sulfate as a solid. Let's say we add that to water. We've talked about how this ionizes. This totally dissociates into its sodium ions and sulfate polyatomic anions. So there's 2 sodiums that are floating around in solution and their cationic state. That's why we call them aqueous. And then there's a sulfate floating around in solution. So if I originally created a 0.35 molar solution of sodium sulfate, and that dissolves into that water, you would actually have 0.7 molar sodium ions and 0.35 molar sulfate ions because of that solution stoichiometry. For every 1 mole of sodium sulfate, you are creating 2 moles of sodium. So that's why we end up doubling the molarity associated with sodium. Anytime you see square brackets around a chemical species, that should be read as the concentration of whatever you're referring to. So for example, if you have Na plus in brackets, you would read that as the concentration of the sodium ion equals, and in this case, 0.70 molar. So we can try a few of those. Let's take a look at chloride ion in a solution that is 1.02 molar with respect to aluminum chloride. So again, we won't have to write this out every single time, but this is what that equation would look like, right? Aluminum trichloride, if it is aqueous, it's going to form 1 aluminum cation plus 3 chloride anions, all aqueous, right? So because of that, if I have 1.02 molar aluminum chloride, that is a 3-to-1 ratio. For every 1 mole of aluminum chloride, I'm creating 3 moles of chloride in solution. So I would take that molarity and multiply it by 3. So the concentration of my chloride ion is equivalent to 3.06 molar. We can do the same thing for B and C. So the nitrate ion in a solution that is 0.451 molar with respect to calcium nitrate. That would be the nitrate ion 0.902. So for every 1 mole of calcium nitrate, you're producing 2 moles of nitrate. So it means that you're going to end up doubling the concentration of nitrate with respect to the calcium nitrate. Similarly, this is kind of in reverse. We have sodium carbonate in a solution in which the sodium concentration is 0.124. Well, in order to create a solution out of sodium carbonate in which the concentration of the sodium cation is 0.124, you would have to halve the concentration. So, come on. There it is. All right. So you have sodium carbonate, so 0.062 molar. Okay. All right, next time we're going to talk about aqueous reactions and chemical analysis. So gravimetric analysis, which is with reference to weight, titration, which is the solution stoichiometry, but it's in a very measured form, special technique called titration. Within titration, we have equivalence point, indicators, and then a strange type of titration called redox titrations, utilizing a redox reaction, as opposed to the titrations that we will deal with, which are all acid-base titrations.